Hi, I'm Old Dog Charles. Welcome to this Fundamental Aspects of Electrical Engineering. This is part 4, where I'm going to talk about direct current and alternating current. So here's an introduction, traditional to include an introduction. So this is all I'm going to talk about. It's not much, it's only 2 things. So there's 2 types of current. We have direct current, which we call DC, and there's alternating current, which we call AC. And they're used in different applications, and I'll talk more in later videos about what these applications actually are. Direct current comes from batteries, fuel cells, dynamos, solar panels, or rectifiers, and kind of crap like that there. The voltage in a DC circuit is constant. Well, more or less. If you change the load, the voltage can fluctuate, and there's times and places where the voltage isn't constant, but we'll talk more about those in a later video. The current really only flows in one direction, so here you can see the current, and it's only flowing in one direction. DC is described by just using the voltage. For example, 750 volts DC. It's typical on tramways and sort of metros. Alternating current can come from rotating alternators or electronic inverters. The voltage is always changing from positive to negative. Current flows one way, and then the other way, and then back again, and then the other way, and then back again, and then the other way, and so on and so forth ad nauseum. The frequency describes how many times the current reverses in 1 second, and the faster this reversal of current occurs, the higher the frequency. So you can see here in the upper wire, the current is going back and forth quite slowly, so it's a lower frequency, and at the bottom, the current's reversing much quicker, so that's like a higher frequency. The period is the time taken for one complete cycle, and you can see here that the period starts when the voltage crosses 0, and then it goes down into the negative, back across 0, and up to the positive, and then back down to 0. That's the period. Frequency is defined as 1 divided by the period. The number of cycles per second is referred to as hertz, and we shorten that to just Hz, and it's named after Heinrich Hertz, who's the father of contact mechanics, which we'll learn about more in a future video. When we talk about AC, we describe it by using both a voltage and a frequency. For example, 15 kilovolts at 16.7 hertz, which is a common electrification voltage in parts of Europe. Except when it's the normal domestic frequency, and then we just talk about it's 230 volts or whatever it is that comes out of your normal plug at your house. There's a problem when we try and measure the voltage and current in an AC circuit. So which value do we actually use? Do we use the peak value? Well, the problem is the peak value only occurs instantaneously twice per cycle. We could use an average, but the average value of an AC waveform is 0. There's as much above in the positive as there is in the negative. The average is going to be 0. So we need to find a different way. That different way is what we call the root mean square, or the RMS. What it is, it's an average taken without any sign. The way we calculate it, the first thing we do is we square the values, so that puts everything on the positive side of the voltage. Then we take an average value of that, and then we take the square root of that average value, and that gives us the RMS. The RMS value is the equivalent if it was in a DC circuit. For a sine wave, the RMS is the amplitude divided by the square root of 2. If you use a voltmeter, it gives you the RMS value, and the amplitude is the square root of 2 higher. So the British domestic voltage of 230 volts actually has an amplitude of 325.52691 volts. Like I said, voltmeters read the RMS value, and the amplitude has to be read by an oscilloscope. If you're buying electrical shit, you need to make sure that the components are rated for the amplitude because it's higher than the voltage that the voltmeter will give you. There's a relationship between rotation and a sine wave. We call this a phasor diagram. So you can see the rotating phasor, which is the voltage, and it goes around in a circle and then projected from that along a time axis, or the angle of rotation, is the instantaneous voltage, which is a sine wave. There's formulae for working all that out. You probably never need the formulae. If you need them, yeah, there they are. And in the formulae, omega is the rotational speed of the phasor in radians per second. 2 pi is 2 pi. F is the frequency. T is time. Here's a recap. This is all the shit that I've kind of talked about. That's all. Very short talk. We'll carry on later and talk about more complicated things in much longer talks. Yeah, I think that need be all.